Hello there, and welcome to the Sleepy Space Channel. Tonight, the unsettling, oddly moving truth about two small machines drifting in the dark. In 1977, the planet that built them sent them outward with the full knowledge that they would never return. 5 years was the promised mission. Nearly 50 have passed, and both probes are still out there, still transmitting, still finding things nobody expected, that the rings of Saturn are slowly disappearing, that a small moon of Jupiter is the most volcanic body in the solar system, that the edge of the sun's bubble does not behave the way the textbooks said it would, and that the planet that built them is a single pixel of pale blue light in a much larger frame. Tonight, the long, quiet story of what Voyager found, told slowly, from the first idea to the long drift afterward. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The door that was only open for a moment. Every part of the story we are about to walk through rests on a single piece of orbital geometry that almost never repeats. The arrangement of the outer planets that made the journey possible occurs roughly once in every 176 years. Before the late 1970s, the last such arrangement had passed during the era of the early American Republic, when no instrument capable of using it existed. The next, if it had been missed, would not return until late in the 22nd century, long after every working scientist of the era had died. The arrangement itself is simple to describe. The 4 outer giants, Jupiter, Saturn, Uranus, and Neptune, would, across a stretch of just a few years, line up in a long curving arc on the same side of the Sun. From a starting point inside that arc, a single probe could swing from one giant to the next, drawing speed and direction from each planet's gravity in turn, without burning new fuel for any of those redirections. Each planet would, in effect, throw the probe to the next. The geometry was a kind of natural ladder reaching out into the dark, and it would be standing there for only a few years on either side of 1977. The discovery of the alignment was made by a young researcher working on routine spacecraft trajectory calculations in the late 1960s. He noticed the curve while tracing the long-term positions of the outer worlds on graph paper, and recognized at once what it meant. Within a few months, the proposal had a name. The aerospace agency that received it called it the Grand Tour. Its scope was vast, a single mission to every giant planet of the solar system, every major outer moon, every ring system, every magnetic field, every face of the deep solar system that had until then been a smear of light in a telescope. The budget proposal that accompanied it was equally vast, and the legislature that received it considered the cost too high. The full Grand Tour, as imagined, was cancelled before any hardware was built. What survived was a smaller version of the original idea. 2 probes, each designed to last for at least 5 years, would be launched within weeks of each other on a careful study of Jupiter and Saturn. The official mission ended there. But the engineers given the task of building the probes made a quieter set of choices. They specified power sources that would decay slowly across decades rather than years. They built in extra thrusters and extra computers and extra backup paths through every critical subsystem. They installed instruments calibrated for environments far beyond Saturn. They argued, in the language of engineering margins, for a mission that nobody had yet agreed to fund. The instruments themselves would, in the early plans, be removed as soon as the official 5-year mission was complete. The engineers ensured the instruments would still work if that decision was reversed. The result was two machines built for an unofficial mission that almost nobody publicly admitted to designing for. They were robust where the budget asked for adequate. They were redundant where the budget asked for simple. They carried instruments calibrated for cosmic environments far beyond the official targets. They were, in the most stubborn and quiet sense, an engineering insurance policy against a future the agency had not yet been persuaded to commit to. On August 20th, 1977, the first of the two probes lifted off from a launch complex on the Florida coast. The probe was numbered 2 because of the order of mission planning, but it was the first to fly. 2 weeks later, on September 5th, its sibling followed. Despite leaving second, the second launched probe was placed on a faster, shorter trajectory through the inner solar system. By December of that same year, it had overtaken its sibling and become, in trajectory terms, the leading craft. The two probes would never meet again. Their paths would diverge through the planets and then through the dark beyond, and they would continue diverging for as long as either of them continued to function. The launch rocket was an evolution of the launch vehicle developed for the early lunar missions of the previous decade, modified for the long climb out to the orbit of Jupiter. The probes themselves rode in a protective fairing on top of the rocket until they were clear of the planet's atmosphere, at which point the fairing was discarded and the probes deployed their antennas, instrument booms, and magnetometer arms. Each of those deployments was its own small drama. Each had a backup mode. Each had a contingency plan in case the primary deployment did not succeed. All of them worked. Within weeks, the probes were past the orbit of the Moon, then past the orbit of Mars, then heading into the long, quiet stretch between the inner and outer solar system known as the asteroid belt. The belt was the first major test. Models of the time were uncertain how many small bodies might pose a real hazard to a spacecraft passing through. The probes crossed the belt without incident, and the modelers updated their estimates downward. From there it was a longer, quieter haul, more than a year of cruise, with the probes powered down to a near hibernation state to conserve their generators. They held their dishes toward Earth and waited. The agency that had built them had committed to 5 years of operations and 2 of the 4 outer worlds. The engineers, more quietly, had built for everything. There is a particular kind of human decision visible in the choices that produced these probes. A decision to design for the maximum rather than the minimum, in a place where nobody else will see the design choices and where the people making them will not live to be praised or blamed for them. The probes themselves know nothing of this. They simply work. But behind their work is a long, quiet chain of decisions made decades ago by people who looked at a narrow window in the geometry of the planets and decided to build something worthy of it. The window opened in 1977. The probes were ready. They went through. To understand how unusual the geometry was, it helps to picture the orbital periods of the outer planets in plain terms. Jupiter takes about 12 Earth years to complete one circuit of the Sun. Saturn takes roughly 29.5 years. Uranus takes 84 years. Neptune takes 165. The 4 planets move at different speeds along nested orbits, and most of the time they are scattered in different directions around the Sun, with no useful arrangement between them. The fact that they happen to line up neatly only once every 176 years is not a coincidence. It is the natural beat frequency of those 4 periods, the long, slow drumbeat of the outer solar system. The probes were timed to step onto that drumbeat at exactly the moment it returned. The young researcher who first noticed the alignment was not searching for a grand tour. He was working on a routine assignment, calculating possible mission trajectories for future spacecraft to single planets. The patterns surfaced in his graphs almost by accident, as a curious confluence of curves rather than a single dramatic insight. The moment of recognition has been described, in interviews, as quiet, a slow understanding that the lines on the page meant something far larger than the single-planet missions he had been asked to study. The proposal he wrote afterward was concise. The orbital geometry would not return for almost 2 centuries. If the planet was going to use it, the planet had to use it now. The full grand tour, as originally imagined, would have launched 4 probes, 2 to the outer giants by way of Jupiter and Saturn, and 2 on a different trajectory to Jupiter, Uranus, and Neptune. The redundancy was intended to ensure that even if half the probes failed, the planet would still get its first close look at every giant. The agency that received the proposal liked it. The legislature that funded the agency did not. The cost was, in the era's dollars, several billion. The full mission was cancelled before any hardware was constructed. What replaced it was a more modest mission, funded for a more modest budget. 2 probes. A primary 5-year mission to Jupiter and Saturn. An extended mission to be considered only after the primary mission had completed successfully and on time. The agency's own engineers, knowing they would never be allowed to officially design for the extended targets, designed for them anyway. The instruments calibrated for Uranus and Neptune were quietly included in the manifest. The power budget planning was extended through decades rather than years. The communications subsystem was designed to work at signal strengths so faint that no contemporary mission required them. The engineers knew, in a way that was never publicly acknowledged, that they were building for the Grand Tour in everything but name. The launches themselves were not without drama. The launch vehicle assigned to the first of the 2 probes, the probe numbered 2, in the official mission designations, was a modified version of an earlier rocket family, fitted with an additional upper stage to give the probe the speed needed to reach Jupiter on a useful timetable. The launch on August 20th was, in the language of the agency's flight controllers, nominal. The second launch, 2 weeks later, was less so. During ascent, the second probe's attitude control system briefly read errors that suggested the probe was tumbling. The errors turned out to be a software interpretation issue rather than a real problem. The probe was performing well within its tolerances. But the engineers on console did not know that for several long minutes. Both probes reached their planned interplanetary trajectories successfully. From that point on, the next phase of the mission belonged to the engineers waiting for the planets to come into view. The cruise from Earth to Jupiter took just over a year and a half. During that period, the probes performed in-flight checkouts of their instruments, calibrated their cameras against known stars, and tested their attitude control systems. Most of the time, both probes were quiet. Their dishes pointed back toward the planet that built them. Their power consumption was kept low. The asteroid belt, which they crossed in the second half of 1978, did not damage either of them. The risk had been weighed and accepted, and the belt turned out to be even emptier than the most optimistic pre-mission models had suggested. The probes emerged on the far side of the belt unharmed, with their instruments intact, with their generators still well within nominal output, with the long stretch toward Jupiter ahead of them. There is something quietly fitting about the role gravity itself played in the entire plan. Each planetary encounter that followed would draw additional speed and direction from the planet being studied, not by burning rocket fuel, but by the simple mechanics of orbital mechanics. The probes would arrive on one trajectory, swing through the planet's gravity well, and depart on a different trajectory, at higher speed, relative to the Sun. The acceleration came entirely from the planets themselves. The planets gave a small portion of their orbital energy to the probes in each encounter, and the probes carried that energy outward to the next encounter. The arithmetic is precise. The planets were paying, in tiny, invisible installments from their own orbital energy, for the journey of two small machines through their family. The two probes, identical in design, were assigned official numbering reflecting their planned mission order rather than their actual launch order. The probe, designated Voyager 1, was originally intended to be the more aggressive of the two trajectories, taking the faster path to Jupiter and Saturn, with the option of being redirected to Titan during the Saturn encounter. The probe, designated Voyager 2, was on the slower path, intended primarily as a backup, but with the engineering capability to continue onward to Uranus and Neptune if everything went well. The actual launch order swapped the two by a few weeks, but the trajectory assignments and the official numbering held. Voyager 1 would visit Jupiter and Saturn, then exit the planetary plane. Voyager 2 would visit all four giants if the mission lasted long enough. Both were already, on the launch pad, the most distant journeys ever planned by the species that built them. There is, in retrospect, a quiet wisdom in the agency's decision to fund only the smaller version of the original plan. The full Grand Tour, with its 4 probes and its years-long sequence of planetary studies, would have been the largest single mission the agency had ever attempted. A failure of the full mission would have absorbed an enormous fraction of the planet's spaceflight resources for very little return. The smaller 2-probe mission, by contrast, could absorb a single launch failure or a single mid-mission anomaly and still return significant science from the surviving probe. The redundancy was, in part, a hedge against the possibility that the full plan would not work at all. The hedge proved unnecessary. Both probes succeeded. Both reached every target on their official schedules. Both have continued long beyond the original mission lifetimes. But the agency's caution, looking back, was the kind of caution that allowed the program to exist in any form at all. Part 2. 2 machines built to outlive their generation. Each Voyager probe is, by the standards of any modern device, primitive. The processors aboard handle vastly less data than a contemporary digital wristwatch. The onboard data storage system is built around magnetic tape, 8 tracks of it, wound onto reels and read by mechanical heads, a technology already considered old at the moment of launch. The radio dish at the heart of each probe is 3 7/10 meters across, a curved metal parabola designed to focus a signal too faint to detect with any other instrument the planet had at the time. The cameras are based on Vidicon tubes, the analog imaging method that had been the standard of broadcast television in the previous decade. None of this was state-of-the-art in 1977, and none of it has been state-of-the-art since. What it is, instead, is durable. The probes were not built to be clever. They were built to last in conditions that no laboratory could fully simulate, to withstand temperature swings of well over 100 degrees, intense radiation in the magnetospheres of the giant planets, the impact of dust grains at relative speeds high enough to puncture lesser shielding, and the slow grind of decades in the cold dark between things. The design philosophy was redundancy at every layer. 2 main computers, with 2 backup computers behind them. 16 thruster jets per probe, 8 primary and 8 backup. 2 attitude control systems. 2 communication paths through the antenna feed. Spares for spares. Heaters around every component that could not survive without them. Even the radio receivers themselves had backup paths, so that if one channel failed, another could be brought online with a single command. Power for each probe comes from a device called a radioisotope thermoelectric generator. The principle is simple in the description, complex in the execution. A small quantity of plutonium-238, sealed inside a heavily shielded cylinder, decays steadily over time. The decay produces heat. The heat is converted, through a thermocouple arrangement, into a flow of electricity. The arrangement has no moving parts. It does not require sunlight, which would have been useless at the distances the probes were headed for. It does not run out quickly, because plutonium-238 has a half-life of nearly 88 years. At launch, each generator produced roughly 157 watts of electrical output, about enough, in terrestrial terms, to run a pair of household light bulbs. That was more than the probes needed to do their full work. The margin would be used, over time, to keep operating as the output declined. Over the decades, that decline has been steady. Each year, the generators produce a few watts less than the year before. The engineers, in response, have switched off instruments one by one in a careful sequence determined by which sensors carry the most scientific weight at any given stage of the mission. The dedicated cameras went quiet first, in the early 1990s, when the probes were well past the planets and there was nothing more for them to photograph. Infrared spectrometers, ultraviolet sensors, plasma instruments followed in their own sequence over the following decades. What remains on each probe today is a small set of instruments studying the local interstellar environment, magnetic field sensors, plasma wave detectors, cosmic ray instruments, drawing the smallest possible currents from a generator, now decades past its initial output. The reliability of the engineering has been demonstrated in ways nobody could have rehearsed. The primary attitude thrusters on one of the probes, after 37 years of nearly continuous use, began to lose efficiency from accumulated wear. The thrusters are not, in any human sense, large. Each fires for a few milliseconds at a time, hundreds of times a day, to keep the probe's dish pointed precisely back toward the Earth, across light hours of distance. The wear was not in the firings themselves, but in the slow buildup of residue around the small nozzles through which the propellant escaped. Engineers, working from light hours away, sent commands to switch over to the backup thrusters. The backups had not fired a single time since the probe was built. They had been carried unused through the asteroid belt, past Jupiter, past Saturn, across the boundary of the solar wind, and into interstellar space. When the new commands arrived, the cold backup thrusters lit on the first attempt. They performed within the same tolerances as the primary set. They held the spacecraft's orientation steady. They are still in use today. A few years later, one of the probes began transmitting a stream of meaningless numbers telemetry that resembled the static of a snowstorm rather than navigation data. The signal itself was clear, the content was not. Engineers traced the fault to a single memory chip on a small circuit board inside one of the onboard computers. Cosmic ray damage had finally caught up with that chip. The probe, sensing the failure in some quiet, automated way, had begun routing some of its data through a backup memory path that itself had a fault. The route was new, the route was broken, the output was noise. The fix, sent across more than 23 hours of one-way communication delay, was a careful set of commands to bypass the damaged chip and use a different routing through working portions of the memory. The probe accepted the new instructions. After the round-trip delay, it returned to clean telemetry on the first attempt. The diagnosis and the fix took months of engineering work. The execution took seconds. The engineers who managed the probes described their work in language that is closer to archaeology than to active design. They work with manuals written in the early 1970s, in handwriting in some cases, on systems whose original designers are mostly no longer alive. They send commands written in command languages that no longer have active users anywhere else in the world. They wait the long hours for replies. They confirm, with each reply, that the small machines are still doing roughly what they were last asked to do. The patience of the work is unusual. The engineers describe it as careful, slow, and deeply rewarding in a way they did not expect when they joined the project. The communication itself is an exercise in patience. The probes transmit at extremely low power, roughly the wattage of a refrigerator light. By the time the signal arrives at the planet that built them, it has spread over an enormous volume of space and is so faint that detecting it requires the largest dish antennas in the world, listening for hours at a time, in a frequency band kept carefully clear of any interference. The data rate is slow. Sending a complete command and receiving a confirmation takes almost 2 full days. The engineers do not work in real time. They work in the rhythm of a tide. What the probes carry, in addition to their instruments, is a phonograph-style record made of gold-plated copper, sealed inside a thin protective cover and bolted to the outside of each spacecraft. We will return to those records near the end of this video. For now, what matters is that they were placed on the probes with the explicit understanding that they would outlast every other component aboard. The engineers building the probes were already, in 1977, thinking in timescales that exceeded the planet's recorded history. These are not sophisticated machines by the standards of what is built today. They are something rarer than that. They are durable ones, and the durability is what has carried them all the way out here. The signal a Voyager transmitter sends back to the planet that built it is, by any ordinary standard, vanishingly weak. The transmitter power, at the antenna, is only about 23 watts less than a household reading lamp. By the time the signal arrives at the planet that built it, it has spread out across an enormous volume of space and is reduced to a power level of roughly 10 to the minus 23rd watts, 23 orders of magnitude, below the original output. To capture a signal that faint, the planet uses arrays of large dish antennas, each one many tens of meters across, scattered across 3 sites around the world to ensure that at least one antenna is always pointing toward the probe, regardless of the planet's rotation. The antennas listen for hours at a time in carefully protected radio bands kept free of interference, and the data trickles in at rates that have been measured in single-digit bits per second for years. The patience required for that kind of communication shapes everything about how the mission is operated. A round-trip command exchange, sending an instruction, hearing the probe acknowledge it, sending a follow-up, hearing the response, takes nearly 2 days. The engineers do not work in real time. They work in sessions that occupy a working week for what, on a terrestrial mission, would be a single afternoon's conversation. Errors are caught long after they occur. Diagnoses are checked across days. Corrections are tested across weeks. The operators describe the work as closer to running a small observatory by mail than to driving a vehicle. The probes themselves are passive partners in the conversation. They do what they are told. They wait for the next instruction. The engineers managing the mission have become, over time, one of the longest continuous engineering teams in the history of space exploration. Some of them joined the program in the late 1970s and have remained on it ever since. Others arrived later, as students or new hires, drawn by the chance to work on something that would outlast every other mission they would touch. The team is small. It has been small for decades. The mission itself, by the standards of its own agency, is inexpensive. Its annual budget today is a fraction of any active flagship mission, and most of the cost is in the time of the engineers themselves rather than in hardware. The hardware, for the most part, was paid for decades ago, and the bills for it are no longer outstanding. The handbooks the team works from are themselves artifacts. Many of the manuals were written in the early 1970s. Some are typed. Some are handwritten in margins. The command language used to control the probes is not used on any other active spacecraft, and the team is among the only places in the world where the language is still actively read and written. When a new engineer joins the mission, part of the first year's work is simply learning the language and the manuals, a kind of slow apprenticeship in a system whose original designers can no longer be consulted directly. The knowledge has been passed forward through 3 generations of operators now, and the lineage is consciously maintained. The instruments themselves have aged in their own quiet ways. Some of them have been through power cycles that have not been used on any active hardware for decades. Others have been carefully kept in narrow temperature ranges to preserve them. The decisions about which instruments to keep alive and which to retire have been made carefully. Each retirement has been mourned in a quiet, professional way by the engineers responsible for that instrument. Each retirement has been written up, recorded, archived, and added to the long account of how the mission is being slowly and patiently ended. What remains aboard each probe today is small. A magnetometer to measure the local magnetic field. A plasma wave instrument to listen for waves in the local plasma. A low-energy charged particle detector to count and characterize particles in the local environment. A cosmic ray subsystem to measure the higher energy particles that come from outside the solar system. A few other instruments at varying states of operation. The total power draw of the remaining instruments is small enough that the probes can still operate them all simultaneously, at least for now. Year by year, however, the budget tightens. The engineers know which instrument will be retired next, in most cases, even before the decision is formally made. The fade is not random. It is being shepherded. There is, in the choices the engineers have made over the decades, a particular kind of stewardship that is difficult to describe in technical terms. The team treats the probes as long-lived patients. They do not push. They do not optimize aggressively. They preserve what is working, repair what can be repaired, accept what cannot, and try, above all, to keep the probes returning data for as long as the data is worth returning. The engineering style is conservative in a way that is unusual on active space missions, where the impulse is more often to do more rather than to do less. The probes are old. The engineers have made peace with that. They are running the mission as gently as they can. The redundancy built into the probes goes well beyond the obvious doubled subsystems. Inside each probe, the wiring itself is laid out so that no single point of failure can disable any major function. Power runs to each instrument through multiple paths. Commands route through multiple processors. Even the timing signals that synchronize the probe's operations are generated by multiple clocks, with the probe able to switch from one to another if a clock drifts out of tolerance. The thinking behind these arrangements was simple. The engineers, working in the early 1970s, could not anticipate every possible failure mode in conditions they could not test on the ground. They could only ensure that no single failure would have outsized consequences. The strategy worked. Across nearly 50 years, individual components have failed on each probe chips, sensors, occasional subsystems, and in every case, the probe has continued to function through alternative paths the engineers had built in decades earlier. The engineers who manage the probes today are, in a meaningful sense, the inheritors of an unusual professional tradition. The original designers, in the early 1970s, made design choices intended for a 5-year mission. The mission has continued for nearly 10 times that long. Each successive generation of engineers has had to learn how to operate hardware whose original constraints they cannot test, whose original calibration data they cannot verify, and whose original design rationale exists only in archived documents written long before they were born. The work of maintaining the mission, year by year, is also the work of maintaining a small body of institutional knowledge that has no analogue anywhere else in spaceflight. The engineers describe the responsibility as humbling. They take it seriously. The probes, for as long as they continue to operate, depend on it. Part 3. Jupiter and the discovery that the solar system is alive. The leading probe reached Jupiter on the 5th day of March, 1979, having crossed 714 million kilometers in a little under 18 months. The trailing probe followed 4 months later. Between them, across the months of their 2 encounters, the probes returned more than 30,000 images of the Jovian system. That was more than every prior mission to the outer solar system combined had returned by something close to an order of magnitude. The pictures changed the working understanding of the largest planet in the solar system almost immediately. Before the encounter, Jupiter was understood as a banded planet. Telescopes of the era had resolved its surface into broad belts and zones, broad parallel ribbons of cloud running around the planet at different latitudes, moving in opposite directions in adjacent bands. The model was orderly. It was also, as the close-up images made clear, a long-distance smoothing of something much wilder. At full resolution, the bands and zones turned out to contain a churning field of vortices, hurricanes, eddies, plumes of warm gas rising and cooling, dark ovals drifting along their own currents, white spots breaking and reforming over the span of weeks. Storms larger than the Earth interacted with storms smaller than continents. The neat banded model was not wrong. It was simply incomplete, in the way a sketch of a forest from a distant ridge is incomplete. The Great Red Spot, already known for centuries as a feature of Jupiter's southern hemisphere, was confirmed up close to be an enormous anticyclonic storm, a counterclockwise hurricane wider than the Earth itself, with smaller white storms orbiting it like satellites. Its color was deep and uneven, varying across the storm's rotating face. The boundary of the storm was sharp where it met certain neighboring bands, frayed where it met others. Around its edges, smaller eddies broke off and recombined, like spray around the edge of a slow, steady wave. The probes followed the spot's rotation for weeks at a time, refining the working understanding of how a storm that large could be stable across centuries. The cameras were not the only instruments that found new things at Jupiter. The probes also confirmed what an earlier flyby had hinted at, that Jupiter has a ring system. Jupiter's ring is nothing like Saturn's. It is a faint, dark, thin band of dusty material around the equator, made of grains so small they reflect almost no sunlight. From the planet's surface, were anyone there to look, the ring would be barely visible at all. From the angle of the approaching probes, the ring caught the light of the sun in such a way that it became briefly visible against the dark. The discovery added Jupiter to the list of planets with rings, alongside Saturn, Uranus, and Neptune, though the rings of those other planets would only be confirmed later in the mission. The probes also detected lightning on Jupiter, flashes seen on the night side of the planet against the dark backdrop of the giant's clouds. They detected aurorae at the poles, glowing curtains of light produced when charged particles funneled along the planet's magnetic field collide with the upper atmosphere. They mapped the planet's magnetic field, which they found to be among the strongest and largest in the solar system. The Jovian magnetosphere, the region of space around the planet dominated by its magnetic field, extends past the orbit of Saturn on the side away from the Sun. The probes flew through layered regions of plasma, charged particles, and energetic radiation, returning the first detailed measurements of the largest planetary magnetic environment in the solar system. The biggest revelation of the Jupiter encounter, however, was not the planet itself. It was its innermost large moon. The moon's name, in the old mythology that planetary scientists have inherited, is the name of a figure briefly transformed by a god. The moon itself, before the probes arrived, was expected to look something like the Earth's own moon. Small, grey, ancient, pockmarked by impact craters frozen in place since the early solar system. What the probes returned was nothing like that. The moon's surface had no impact craters at all. None could be found anywhere on it. Where billions of years of cratering should have been, the surface was painted instead in sulfur yellows, reds, oranges, and pale whites. The dark ovals scattered across the landscape turned out to be volcanic calderas. The other markings, long flat regions of one color or another, were lava flows, fresh enough to still appear geologically young. As the cameras of the trailing probe panned across the moon during its approach, a single image showed something almost impossible. A plume of material rising above the moon's limb, hundreds of kilometers high, caught at the moment of eruption. Over the course of the encounter, several active eruptions were imaged. The moon was not a frozen geological corpse. It was, the engineers and scientists watching the data come in slowly realized, the most volcanically active body in the entire solar system. The mechanism that drives the volcanism was, in itself, a discovery. The moon is locked in a precise gravitational resonance with the next two large moons outward. As it orbits Jupiter, the resonance keeps its orbit slightly elliptical rather than perfectly circular. The result is that the moon swings closer to the giant planet and then farther away on each revolution, and on each closer pass, it is squeezed slightly harder by Jupiter's enormous gravity, then released as it swings outward again. The flexing turns into heat. The heat finds its way to the surface through hundreds of active vents. Some of the eruption plumes reach more than 200 kilometers above the surface, high enough that material from the moon's volcanoes is flung into the surrounding magnetosphere of Jupiter itself, where it forms a faint torus of charged particles along the moon's orbit. The torus was detected, in turn, by the probe's instruments. One discovery led directly to another. The next moon outward, the one with the bright, icy shell, was a revelation of a different kind. Where the volcanic moon was loud and bright in its activity, this next moon was almost silent. Its surface was nearly entirely smooth, a near white shell of water ice with very few impact craters anywhere across it. What it did have, in every direction, was a fine network of long, shallow, brown-tinted lines crossing the ice. Some were straight. Some curved gently. Some intersected in geometric patterns. The lines looked, plainly, like cracks. The probes could not see beneath the shell, but the question their images raised has not gone away in the decades since. Why were the cracks there at all? What was breaking the ice? The leading hypothesis is straightforward to state and difficult to confirm. The moon's icy crust may float on a global ocean of liquid water, kept warm by the same kind of tidal flexing that drives the volcanism of its inner sibling, only at a far gentler level. The cracks would be the surface manifestation of an ice shell shifting slowly above a liquid sea. The relative scarcity of craters would be the slow, steady resurfacing produced by that motion. The probes did not prove the ocean was there. They placed it on the table. The question has driven the planetary science of the outer solar system ever since, and it has not yet been answered. The other two large moons of Jupiter, both larger than the inner pair, were quieter in their stories. The third one outward, the largest moon in the solar system, larger than the planet Mercury, was found to have a surface of mixed, bright and dark terrain, younger ice in the bright regions, older ice mixed with rocky debris in the darker ones. It alone among the moons of the solar system was found to have its own magnetic field, generated by motion in its interior, a small but real magnetosphere within Jupiter's much larger one. The fourth large moon, the outermost of the four, was found to be the most heavily cratered body in the solar system, its surface preserving a record of impact rates that has changed very little since the early days of the planets. Beneath its ancient cratered crust, the moon may also harbor a deep saltwater ocean, though one more isolated and less easily studied than its inner siblings. Beyond the four large moons lay the smaller members of Jupiter's family, dozens of small captured worlds, irregular shapes, distant orbits, and the faint ring of dust the probes had confirmed. The Jovian system, before Voyager, had been a planet and 4 points of light. After Voyager, it was a small solar system in its own right, with active volcanism, possible oceans, multiple distinct geological histories, and a magnetic environment as complex as the planet's atmosphere. None of this had been predicted. All of it became, over the following decades, the foundation of the field of outer planet science. The Jovian magnetosphere itself, sampled in detail for the first time by the probes, turned out to be one of the largest single structures in the solar system. The magnetic field of Jupiter is roughly 20,000 times stronger than the Earth's at the planet's cloud tops. The field is generated by motion in a layer of metallic hydrogen deep in the planet's interior, where pressures are high enough that hydrogen behaves as a conducting fluid. The resulting magnetosphere extends millions of kilometers ahead of the planet on the sunward side, where the solar wind pushes it back and stretches out behind the planet in a long magnetotail that reaches as far as the orbit of Saturn. If the Jovian magnetosphere were visible to the unaided eye, it would appear from the Earth as one of the largest objects in the sky. Inside that enormous magnetic environment, the probes mapped layered regions of charged particles. Near the planet, an intense radiation belt traps high-energy electrons and ions, with intensities so high that any spacecraft passing through has to be carefully shielded. Further out, sheets of plasma trail along the planet's magnetic equator. The volcanic moon of the inner system, the moon with the sulfur-colored surface, supplies the magnetosphere with a continuous stream of material from its eruptions. Sulfur and oxygen ions blown off the moon's surface by collisions with the surrounding plasma form a faint glowing torus, a donut-shaped ring of charged particles encircling Jupiter along the moon's orbit. The torus was detected by the probe's instruments and has been studied by every subsequent mission to the Jovian system. It is a kind of internal weather system for the planet's magnetic environment, driven by the volcanism of a moon whose own activity nobody had predicted. The probe's images of Jupiter's atmosphere also resolved a feature that has been studied closely ever since. Among the smaller storms in the planet's southern hemisphere, the probes imaged a series of long-lived white ovals that orbited around the Great Red Spot for decades. The ovals were named, at the time, by simple letters of the alphabet. Over the years that followed, the ovals merged in pairs, then merged again, until only a single white storm remained itself, eventually changing color and being given a new informal name. The observation of those mergers, conducted by ground-based telescopes in the years and decades after the probe's encounters, depended directly on the precise photometric calibration the probes had supplied. Without the probe's images as reference, the long campaign of measuring Jupiter's atmospheric behavior would have lacked its baseline. Beyond the 4 large moons, the probes also returned the first detailed images of several smaller, irregular moons of Jupiter. Some of these are clearly captured asteroids, with surfaces showing the cratering and irregular shapes typical of small bodies that formed elsewhere in the solar system and were later trapped by Jupiter's gravity. Others orbit in retrograde fashion, suggesting they were captured from the outer solar system rather than formed alongside the planet. The probes did not have the time to study any of these small moons in detail, but the images they returned added these objects to the catalogue of the solar system, where they have been studied incrementally ever since by larger telescopes from the Earth. What the Jupiter encounters established, more than any single discovery, was a new working principle for outer solar system science. Before the probes, the outer planets had been treated, by default, as comparatively static large gas envelopes around uncertain interiors, with moons that were small and inert. After the probes, the outer planets and their moons became, in the working scientific imagination, places that are actively doing things. Storms are running. Volcanoes are erupting. Oceans may be hiding beneath ice shells. Magnetospheres are interacting with the solar wind in ways nobody had measured directly. The default expectation flipped. Whatever else the planet that built the probes might find at the outer worlds, it would not find them quiet. The encounters themselves were over within weeks. The leading probe spent only a few days at close range to Jupiter before its trajectory carried it away towards Saturn. The trailing probe followed a similar timetable 4 months later. In the hurry of the close approaches, the probes returned more data than any prior mission to the outer solar system, but they could not stay. The mission designers had chosen the trajectories to make the most of the planetary alignment, and the alignment meant motion. Each probe was moving at velocities of tens of kilometers per second relative to Jupiter, and the planet's gravity bent their paths only briefly before flinging them onward. The encounters were a single long flyby in which the probes could not pause. Every image, every spectrum, every magnetic field reading, every plasma measurement had to be made on the fly during the brief window when the probes were close enough to gather useful data. The encounters were short. The consequences have lasted decades. The images themselves arrived back at the planet that built the probes in a slow, steady stream that lasted weeks. The probes did not transmit continuously. They stored their data on the 8-track magnetic tape recorders and played it back when their dishes had a clear line of sight to the listening antennas. The pictures arrived one line at a time, with each full image taking minutes to assemble. The engineers and scientists on the planet sat in mission rooms watching screens fill in line by line, the surface of Jupiter slowly resolving into clouds and storms and color as the data came in. The pace of discovery during the encounters was set by the bandwidth of the radio link rather than by the speed of the probes themselves. Each new image was a small event. Each new image carried, in many cases, something the working models had not predicted. The mood in those rooms, by the accounts of the people who were there, was one of slow, steady amazement that lasted for weeks at a time. Part 4. Saturn, and the rings that are slowly disappearing. The leading probe reached Saturn in November of 1980, 3 years and 3 months after its launch from the Florida coast. The trailing probe arrived 9 months later. Both encounters were brief, only a few weeks each at close range, with the probes moving at relative speeds high enough that the close approach phase passed in days rather than weeks. But the data they returned, in those few hurried weeks, overturned the working understanding of planetary rings as thoroughly as Jupiter had overturned the working understanding of gas giant atmospheres. Before Voyager, telescopes from the Earth had resolved Saturn's ring system into roughly 5 major rings, broadly separated by dark gaps, each ring believed to be a relatively uniform disk of ice and rock. The probe's close-up images revealed that the 5 major rings were not 5 at all. They were hundreds of thinner ringlets, packed tightly together inside each broad band, each ringlet with its own slight variation of width, density, and composition. The resolution kept pulling structure out of structure out of structure. The longer the cameras looked, the finer the divisions became. A piece of music heard from very far away resolves into individual instruments only as the listener moves closer. Saturn's rings, seen up close, resolved into individual voices the same way. Inside the rings, the probes found shepherd moons, small moons, orbiting at the edges of certain rings, their gravity pinching the ring material into sharp boundaries. They found density waves, spiral patterns, rippling outward through the rings, set up by gravitational resonances with the larger inner moons. They found gaps within gaps, faint outer rings nobody had detected, ringlets that intertwined like braided ribbons in defiance of any simple model of orbital mechanics. They found a faint outer ring, designated by a single letter that had not previously been used in the alphabet of Saturn's rings, and they imaged it for the first time. They also found something stranger. Across the broad inner ring known by a single letter near the start of the alphabet, dark radial spokes of fine dust would drift across the ring's surface, features that should not, by orbital mechanics alone, have been stable for more than a few minutes, because the inner edge of the ring moves faster than the outer edge, and any radial feature should be sheared apart almost immediately. The spokes, instead, persisted for hours at a time. They drifted slowly, as though carried by something other than orbital motion. The leading hypothesis is that fine dust grains, electrostatically charged by solar radiation and the planet's magnetic environment, briefly lift above the ring plane and travel along magnetic field lines rather than along orbital paths. The exact mechanism is still being studied. The probes were the first instruments to see the spokes at all. The most quietly remarkable Saturn finding, however, was something the probe's instruments suggested rather than imaged directly. The probes detected a continuous, faint, inward flow of charged particles from the rings into the upper atmosphere of the planet. The flow was small at any given moment. Integrated across the surface area of the rings, integrated across long timescales, it added up to a significant slow loss of ring material into Saturn itself. The implication, refined later by other missions, is that the rings are not permanent. They are slowly raining inward that the most iconic feature of the most photogenic planet in the solar system is, on long enough timescales, draining away into the planet beneath. The current estimates suggest that the rings will be substantially eroded on a timescale of a few 100 million years. The rings are, on cosmic terms, young, likely much younger than the planet itself. And they will not be there forever. The planet that built the probes happens to be alive at a moment when Saturn briefly wears a ring. The next observers, however distant, may not see it. The probes were the first to detect that quiet inward flow. Among the many moons of Saturn, the probe's close attention fell on 2 in particular. The first was the largest. The moon was already known to possess an atmosphere. A previous flyby probe had detected the haze around its limb on its way through the Saturn system. The Voyagers confirmed the atmosphere and characterized it for the first time. The atmosphere was thick. At the surface, it was denser than the atmosphere of the Earth. Its composition was dominated by nitrogen, with a small but significant share of methane, and a long list of more complex carbon-bearing molecules in trace amounts. The combination was unique. No other moon in the solar system had been found to carry a comparable atmosphere. The closest analogue anywhere was the early Earth, where nitrogen was also the dominant atmospheric gas, and where carbon chemistry was just beginning to organize itself into more complex forms. The moon was not the Earth. It was far too cold for liquid water to exist on its surface. But the chemistry was running. The atmosphere was active. Ultraviolet light from the sun was driving slow reactions among the carbon-bearing molecules in the upper layers, and the products of those reactions were settling, in some places, as reservoirs of carbon-bearing material on the ground. The probes could not see through the thick orange haze of the moon's atmosphere to its surface. The haze itself was the product of the chemistry. The cameras returned images of a smooth, featureless ball of light against the dark, the haze hiding everything beneath. Decades later, another mission would drop a small probe through that haze and find, beneath it, an alien landscape of methane rivers, methane lakes, dunes of organic sand, and rain falling slowly through a sky, the color of pale honey. The Voyagers did not see those things. They only opened the door. The second moon, to draw the probe's close attention, was much smaller. It was a small, bright moon, only about 500 kilometers across, orbiting at one of the inner edges of Saturn's ring system. The first close images showed two distinct types of surface on this moon, side by side. One half of it was heavily cratered ancient terrain, the kind of surface typical of any inert, icy body in the solar system. The other half was smooth, young, almost crater-free, as though something had recently resurfaced it. The contrast was extreme. The two terrains met along sharp, visible boundaries, with no apparent gradient between them. Such a discrepancy on a single small moon is hard to explain. The standard expectation for a body that small is that it should be geologically dead too small to retain internal heat for long after formation. The moon, plainly, was not dead. Something was renewing its surface. The probes could not identify the mechanism. They left the question on the table, just as they had with the cracked, icy shell of the inner Jovian moon. Decades later, a long-duration orbiter at Saturn flew close enough to find what the Voyagers had hinted at. Geysers were erupting from cracks near the moon's south pole, shooting plumes of water vapor and ice particles hundreds of kilometers above the surface, feeding directly into one of Saturn's outer rings. Beneath the ice was a global ocean of liquid water, kept warm by tidal flexing, in much the same way as Europa's suspected ocean and the volcanic moon of Jupiter's inner system. The Voyagers did not see those plumes. But the strangeness of the surface they imaged was what made it possible, 20 years later, for another mission to know exactly where to look. Saturn itself, beyond the rings and the moons, also gave up some of its secrets to the probes. The planet's atmosphere was found to be banded like Jupiter's, with weather patterns less dramatic, but with winds at the equator faster than anything seen on its larger sibling. The planet's magnetic field was found to be unusually well aligned with the planet's rotational axis, to a degree that has puzzled magnetohydrodynamic modelers ever since. Lightning was detected. Aurorae were imaged at the poles. The probes confirmed that Saturn radiates more heat than it receives from the Sun, and pieced together a working model of how that internal heat is generated partly leftover heat of formation, partly the slow gravitational separation of helium from hydrogen deep in the planet's interior. Each of these findings, on its own, would have been a notable result. Together, in the brief weeks of the encounters, they amounted to a wholesale rewriting of what was known about the second largest planet in the solar system. After Saturn, the two probes' paths diverged for good. The leading probe had been redirected during its Saturn flyby to pass close to the Moon with the thick atmosphere. The trajectory required for that pass bent the leading probe's course up and out of the plane of the solar system. From that point on, the leading probe would no longer visit another planet. It would climb steadily northward, out of the disk in which the planets orbit, and into a region of the heliosphere that no spacecraft had ever sampled before. The trailing probe, by contrast, had been placed on a trajectory that kept it inside the plane of the solar system. It had been threaded carefully through the geometry of the outer worlds in such a way that it could continue on, alone, to Uranus and then to Neptune. It would take another 5 years to reach the first of those two worlds. There would never be another spacecraft sent to either of them. The Grand Tour, in its smaller surviving form, was still in progress. Saturn itself, beyond the rings, presented the probes with a planet substantially different from Jupiter despite their broad family resemblance. The atmosphere was banded, but the bands were broader and less colorful than Jupiter's. The colors were softer pastels rather than the deeper ochres and reds of the larger giant. The storms, when the probes found them, were smaller and shorter-lived. But the wind speeds at Saturn's equator were far higher than anything seen on Jupiter. The equatorial jet stream on Saturn was measured by the probes at roughly 1,800 kilometers per hour, the fastest equatorial winds known on any planet in the solar system at the time of the encounters. The mechanism driving such fast winds on a planet so distant from the Sun remains, even now, a partly open question. The probe's wind measurements were the first direct calibration of the working models. Saturn's interior, like Jupiter's, was inferred rather than seen. The probe's gravity measurements, combined with their tracking of the planet's magnetic field, suggested an interior structure with a small, dense core, a thick layer of metallic hydrogen surrounding it, and an outer envelope of molecular hydrogen and helium. The planet's slow internal contraction over billions of years releases gravitational energy as heat, and the probes confirmed that Saturn radiates more energy than it receives from the Sun. The slow rain of helium droplets through the planet's interior, separating from the surrounding hydrogen at the high pressures of the deep envelope, also contributes a steady internal heat source. The probe's instruments, working from the outside in, were the first to provide direct support for the working models of how a giant planet generates and stores its own internal heat over geological time. Among Saturn's moons, beyond the two singular cases of the atmospheric moon and the geologically active moon, the probes also returned the first close images of several other large icy bodies. One of them carries an enormous impact crater on its surface, large enough that the structure of the crater dominates the moon as a whole. Another shows long parallel ridges across one hemisphere, suggesting some kind of past tidal flexing or rotational stress. Another is one of the brightest objects in the solar system by reflectivity, its surface coated in fresh ice that may itself be debris from the geyser-bearing inner moon, lofted into the outer rings and then dusted across the surfaces of nearby moons. A fourth has two distinct hemispheres, one bright and one dark, with a sharp boundary running around the moon's equator. The cause of the boundary is still being investigated. The moons of Saturn, when the probes arrived, had been a small number of named bodies. By the time the probes left, they were a system of geologically distinctive objects, each with its own history, several with their own active questions. The number of moons in the Saturnian system grew too. The probes identified several previously unknown small moons during the encounters. Some of them are the shepherd moons mentioned earlier, holding rings in place. Others are co-orbital moons, sharing the same orbit at different angles and exchanging places periodically through gravitational interactions. The count of Saturn's moons increased significantly during the encounters and continued to grow afterward as ground-based observations refined the totals. Saturn's auroral physics, sampled by the probe's ultraviolet instruments, also revealed unexpected detail. The auroral ovals on Saturn turned out to behave in ways related to the planet's magnetic environment in a manner subtly different from the Earth or Jupiter. The auroral light shifted with the planet's rotation, suggesting that Saturn's magnetic axis is nearly perfectly aligned with its rotational axis, a configuration that, by the working understanding of how planetary dynamos generate magnetic fields, should not be possible. A dynamo running in a turbulent conducting fluid normally produces a field with at least some tilt relative to the rotation axis. Saturn's alignment, to within a small fraction of a degree, suggests that something inside the planet is filtering the field, that there is a layer somewhere in the interior, stable and stratified, that smooths out the asymmetries before the field reaches the surface. The mechanism is still being studied. The probes were the first instruments to record the alignment in enough detail to make the question precise. The Saturn encounters, like the Jupiter encounters, were brief at close range. The leading probe was at Saturn for only a few days, near closest approach. The trailing probe's encounter, 9 months later, was similar in duration. In those few brief days, the probes returned tens of thousands of images and made measurements that have shaped Saturn's science ever since. The two encounters together established Saturn as a planet of layered complexity, beautiful at a distance, intricate up close, governed by dynamics that the planet's scientists are still slowly working out. The probes left Saturn behind and continued onward, each on a trajectory chosen years earlier for a particular set of further targets. Voyager 1 climbed up and out of the plane of the planets. Voyager 2 stayed in the disk and aimed itself, with a precision that nobody had attempted before, at the next giant outward. Among the smaller discoveries at Saturn was a careful confirmation of how the planet's rings stay so flat. The thinness of the ring system is one of its most extraordinary properties. The main rings are tens of thousands of kilometers wide, in some places hundreds of thousands, but they are only a few tens of meters thick from top to bottom. The ratio of width to thickness is more extreme than any object the planet that built the probes has ever produced. The mechanism that keeps the rings flat is a combination of orbital mechanics and gentle collisions between ring particles. Particles that drift above or below the ring plane collide with other particles, lose their vertical motion, and settle back into the plane. Over time, the system flattens itself. The probe's images, resolving the rings at extreme angles, made the thinness visible in a way no telescope from the planet's surface had been able to achieve. Part 5. Uranus and Neptune, and the long, lone crossing. The trailing probe reached Uranus in January of 1986, 8 years and 5 months after its launch. The encounter was brief, only a few hours at close range, with the probe passing just over 80,000 kilometers above the planet's cloud tops at high relative speed. But in those few hours, it returned the only close images of Uranus that human beings have ever taken. There has never been another mission to Uranus by any spacecraft of any kind. Everything the planet that built the probes knows about the third giant of the outer solar system from close range was learned during those few hours of close approach. Uranus is the most tilted of the giant planets by a wide margin. Its rotational axis lies nearly in the plane of its orbit, tilted almost 98 degrees from the vertical. As a result, the planet effectively rolls along its orbit rather than spinning upright. At any given moment in its long orbit, one pole faces directly toward or away from the Sun for decades at a time, while the equator and the opposite pole sit in long shadows. The probe arrived at a moment in the planet's 84-year orbit when one pole was facing the Sun directly, and the planet, in the probe's images, was lit almost entirely from one direction. The atmosphere was nearly featureless, a smooth blue-green haze, almost serene compared to Jupiter's vortices and Saturn's banded storms. Decades later, larger telescopes have shown that Uranus does in fact have weather. The apparent calm was an accident of the season. The deeper surprise was magnetic. Uranus has a strong magnetic field. The field is generated, like the fields of the other giant planets, by motion in a conducting layer in the planet's interior. But the field is tilted at roughly 59 degrees from the planet's rotational axis and offset significantly from the planet's center as well. The Earth's magnetic poles, by comparison, are only about 11 degrees from its rotational poles. Uranus's magnetic environment is wildly asymmetric, a field that tumbles as the planet rotates, generating a magnetosphere that twists itself into a corkscrew shape downstream of the planet. The probe's instruments mapped that magnetic environment for the only time it has ever been measured directly. The data has been reanalyzed by generations of modelers since, and many of the questions raised by it remain open. The encounter also discovered 10 new small moons around Uranus, more than doubling the known count, and added 2 faint rings to the planet's known ring system. The rings of Uranus are nothing like Saturn's. They are dark, narrow, made of carbon-rich material rather than bright ice, and difficult to see from the Earth even with the largest telescopes. The probe imaged them as thin ribbons of black against a darker background. They appeared, in the images, almost as line drawings against a charcoal field. Among the larger moons of Uranus, the most striking was one with a name borrowed from a Renaissance play. The moon was small, irregular in shape, and crossed in every direction by ridges, cliffs, and broken terrain. Its surface looked, in the probe's images, as though the moon had been broken apart at some point in its history and reassembled imperfectly. The mechanism is still under investigation. Some models propose an ancient catastrophic collision. Others propose internal differentiation gone partially wrong. Whatever the cause, the moon's surface stands as one of the most chaotically structured in the solar system. After Uranus, the trailing probe continued onward, alone, on the longest single leg of the mission. 3.5 years separated its arrival at Uranus from its arrival at Neptune. During those years, the probe was largely in cruise mode, with most of its instruments powered down to conserve energy. It approached its final planetary target steadily, in the long quiet of the outer solar system, at distances where the Sun itself appeared no larger than a particularly bright star. The probe reached Neptune in August of 1989, 12 years after launch, more than 4 billion kilometers from the Sun, near the practical edge of where the original mission designers had even attempted to plan. The trajectory carried the probe just 5,000 kilometers above Neptune's North Pole. That close approach is the closest any planetary encounter of the mission ever achieved. The probe was, for those few minutes, traveling at a speed and altitude that placed it just outside the upper layers of Neptune's atmosphere itself. Neptune, unlike Uranus, was not quiet. Where Uranus had appeared serene, Neptune was a deep blue planet of storms. A massive, dark, anticyclonic storm dominated the southern hemisphere at the time of the encounter, roughly the size of the Earth. The storm was named, in the convention of the time, for its color and its position. White, cirrus-like clouds drifted high above the planet's deep cloud deck, casting shadows on the deeper layers below. The winds on Neptune, the probe's instruments determined, were the fastest measured anywhere in the solar system gusts, approaching 2,400 kilometers per hour, in a planet so far from the Sun that the warming influence of sunlight is almost negligible. The energy driving those winds appears to come from internal heat, rising slowly from the planet's interior, not from external solar warming. The probe also discovered 6 new moons at Neptune and imaged the planet's ring system for the first time. Neptune's rings turned out to be unusual in a particular way. Several of them are not complete rings at all, but arcs, clumped regions of material that cover only portions of their orbits. Standard orbital mechanics would predict that such arcs should smear themselves out over time into uniform rings. They had not. Later, analysis suggested that small shepherd moons were holding the arcs in place by gravitational resonance, the same kind of effect seen in some of Saturn's rings, scaled down and made stranger by Neptune's odd ring geometry. The probe's final stop in the Neptune system was a flyby of the planet's largest moon. The moon's name, in the same old mythology that has supplied so many planetary names, is the name of a sea god's son. It orbits Neptune backward in the opposite direction of the planet's rotation and is the only large moon in the solar system to do so. The retrograde orbit strongly suggests that the moon was not formed alongside Neptune, but was captured later from elsewhere in the solar system, most likely from the broad population of icy bodies that orbit beyond Neptune. The flyby revealed a strange world. The moon's surface temperature was the coldest known anywhere in the solar system at the time of the encounter, colder even than the surfaces of more distant icy bodies because of the particular chemistry of the moon's surface. It carried a thin atmosphere of nitrogen, hazy and pale, and a surface marked in many places by long flat plains and curious smooth regions. Most strikingly, the probe imaged active geysers near the moon's south pole, shooting nitrogen gas and dark dust kilometers into the moon's thin atmosphere. The moon was, against every expectation for an object that size at that distance, geologically active. The plumes were carried downwind by the moon's atmosphere, leaving long, dark streaks across the surface. After the flyby, the probe pivoted its instruments away from the Neptune system. Its planetary work was finished. It pointed itself toward the long dark ahead and began the part of the mission that nobody had originally planned for. The grand tour, in the form actually flown, was complete. 2 giants. Then 4. Then the final pair, each more distant than the last. From that day forward, both probes were headed for the boundary of the solar system itself, and the boundary did not behave the way the models had predicted. Between the encounters at Saturn and Uranus, the trailing probe spent 4.5 years in cruise. Most of that time was quiet. The probe's primary tasks during cruise were navigational small attitude maneuvers to keep its dish pointed at the planet that built it, small course corrections to refine its trajectory toward the upcoming Uranus flyby. The instruments were largely powered down. The science return during cruise consisted of cosmic ray and magnetic field measurements made in the outer heliosphere, in regions of space that no other spacecraft had yet sampled. Those measurements, collected month by month across years of slow progress, formed a baseline against which the dramatic data from the Uranus flyby could later be compared. During the cruise, the engineers on the planet that built the probe were already planning the encounter. The geometry of the Uranus encounter was tight. The probe would only have a few hours at close range, and its instruments would have to be perfectly choreographed to maximize the science return during those few hours. A long sequence of pre-planned commands, encoded into the probe's onboard computers during a series of careful uploads, would carry out the encounter automatically. The probe would, during the close approach, be too far away for the engineers to manage in real time. The round-trip communication delay alone exceeded the duration of the closest part of the encounter. Once the close approach began, the probe was on its own. Uranus's interior, the probe's instruments suggested, is unlike either Jupiter's or Saturn's. The planet appears to consist mostly of water, methane, and ammonia ices, with smaller fractions of hydrogen and helium, an icy giant rather than a gas giant in the strict sense. The interior may include layers of unusual high-pressure ices, including a form of water ice, in which the molecules behave more like a metal than a liquid. The exact internal structure of Uranus is still being modeled. The probe's flyby provided the only direct measurements of the planet's gravity field, magnetic field, and atmospheric composition that have ever been collected from close range. The encounter at Uranus included a flyby of the planet's larger moons. The probe imaged each of the major moons in turn. The smaller, more chaotic moon, the one with the broken-looking surface, was the most striking. Its surface showed enormous cliffs, some of them many kilometers high, and large rectangular patches of differently aged terrain butted up against each other at sharp boundaries. The leading interpretation is that the moon may have been broken apart by an impact early in its history and reassembled imperfectly, leaving the disparate pieces of its original composition exposed at the surface. The probe did not have time to study the moon in close detail. Its images, captured during a brief window of high resolution, remain the only close-up photographs anyone has ever taken of that moon's surface. After Uranus, the cruise to Neptune was the longest of the mission's planetary legs. 3.5 years of quiet motion through the outer solar system, with the sun shrinking steadily behind the probe. At Neptune, sunlight is roughly 1/900 times fainter than at the Earth. The probe arrived at a planet that, from its own vantage point, was lit by what would, from the planet that built the probe, count as little more than a particularly bright twilight. The instruments had to be calibrated for that lower light. The cameras had to take longer exposures. Every aspect of the encounter had been planned, years in advance, for the particular conditions the probe would encounter at the farthest planet of the solar system. Neptune's interior, like Uranus's, is dominated by water, methane, and ammonia ices, in a structure broadly similar to its sibling. But Neptune is internally hotter than Uranus by a noticeable margin. The planet radiates more than twice as much energy as it receives from the sun, a fact the probe's instruments confirmed during the flyby. The source of that internal heat is still being studied. It may be related to the planet's formation history, or to ongoing differentiation in its interior, or to processes nobody has yet identified. Whatever the source, the heat shows up in the planet's atmospheric dynamics. Neptune's storms and high winds, fueled by that internal energy, are driven from below rather than from above, in a way that no model of the planet has yet fully captured. The flyby of the planet's largest moon, near the end of the encounter, returned the most surprising single set of images of the entire Neptune visit. The moon's surface, in the probe's images, was marked by long, flat regions and curious, smooth zones interrupted by occasional dark streaks and pits. The active nitrogen geysers near the moon's south pole were imaged on the moon's sunlit side, where they were faintly visible against the surface. The probe's instruments tracked the plumes downwind across the moon's thin atmosphere. The moon's geological activity, on a body so cold and so far from the sun, was one of the great surprises of the Voyager mission. The probe could not stay to study it in detail. The flyby took only a few minutes. The moon, like every other planetary target of the mission, has not been visited again. The data returned from Neptune was, in some respects, the most precious of the entire mission. There would be no other mission to either of the ice giants for at least several decades after the encounter. The radio link back to the planet that built the probe was operating at extreme distance, with the signal taking more than 4 hours one way to cross the gap between Neptune and the antennas on the planet. The data rate had been reduced accordingly. Each image took longer to send than the same image had taken from Jupiter or Saturn. The engineers managing the listening antennas had to schedule the highest priority observations carefully, ensuring that the most important images and measurements would be received cleanly before any later, lower priority data. The encounter, in operational terms, was as much a triumph of patient communication as it was a triumph of spaceflight. After Neptune, the trailing probe had no more planetary targets ahead of it. The next major event in its mission would be the crossing of the heliopause, still more than 2 decades in the future. The probe entered a long phase of cruise, during which most of its instruments would be powered down or operated at minimum capacity, and most of its work would be the steady, patient measurement of the solar wind in the outer reaches of the heliosphere. The leading probe, having exited the planetary plane after Saturn, was already several years into the same kind of work. Both probes had, in effect, become the same kind of spacecraft after their planetary tours ended. They had ceased to be planetary probes. They had become deep space instruments, measuring the slow gradients of the outer solar system as they drifted further from the Sun. The transition was not announced. It was simply what the probes were now doing. Part 6. The Pale Blue Dot and the Crossing of the Boundary. By February of 1990, the leading probe was 6 billion kilometers from home. Its planetary work had ended a decade earlier at Saturn. The trailing probe was nearly through its own work at Neptune. The cameras on both spacecraft were soon to be turned off permanently. The instruments still doing real science magnetometers, plasma wave detectors, cosmic ray instruments would need the limited remaining power, and there was nothing left to photograph that any camera could resolve at the distances now involved. The decision to retire the cameras was a practical one, and within the mission, it had already been made. One scientist on the mission team had been advocating for years, before the cameras were finally turned off, for a single last image. He had argued the case at meetings, in memos, and in informal conversations. He wanted the leading probe to be turned around, briefly, to look back the way it had come, and to photograph the inner solar system from the farthest vantage point any human-made object had ever occupied. The argument was not scientific. The pictures would not contain new data. The argument was that the act itself mattered, that to see the Earth from the outer edge of the planetary system would change how the planet was understood by the people who looked at the resulting image. After several years of delay, the mission directors agreed. On the 14th of February, 1990, the leading probe rotated. Its narrow-angle camera pointed back toward the inner solar system. It took a sequence of images, 60 in all that, stitched together, formed a wide panorama of the place the probe had come from. Among those images was one, taken in the direction of the Earth, in which the Earth itself appeared as a single bright pixel, less than 1/10 of a pixel wide, sitting inside a narrow band of light scattered by the camera's own optics. That image has come to be known by a short and quiet name. The dot of pale blue light in the photograph is the entire planet on which the probe was built, seen from a distance equivalent to roughly 34,000 Earth diameters. Everything that has ever happened in the history of human civilization took place on that dot. Every empire, every language, every act of love, every act of cruelty, every piece of music, every quiet evening. The entire human record occupies less than 1/10 of 1 pixel in a single photograph taken from 6 billion kilometers away. The photograph is not a scientific record. It is a mirror held up at an enormous distance, showing the planet what it looks like from outside its own context. Once seen, it is difficult to forget. Shortly after the panorama was complete, the cameras on both probes were switched off permanently. The probes still had instruments, and the instruments still had power, but the work that remained was no longer the kind of work that could be photographed. The pictures had been taken. The story now turned to the long crossing of the boundary that separates the sun's bubble from everything outside it. Beyond the planets, the probes entered a region nobody had ever measured directly. The sun blows a continuous stream of charged particles outward into space, in every direction, at supersonic speed. This stream, the solar wind, defines a bubble around the entire solar system, inside which the sun's magnetic field and the sun's particles dominate the local environment. Outside the bubble is the interstellar medium, where the magnetic field and the particles of other stars take over. Models of the bubble had been built for decades, but no spacecraft had ever crossed it. Both probes were now headed for that crossing. The boundary was understood to be made up of 3 distinct surfaces, layered one inside the next. The first surface is the termination shock, the place where the solar wind, blowing outward at supersonic speed, runs into enough resistance from the interstellar medium that it abruptly slows, becomes turbulent, and begins to pile up. The second is the heliosheath, a thick, turbulent region of slowed solar wind extending outward from the termination shock. The third is the heliopause, the outer boundary of the heliosheath, the actual membrane separating the sun's bubble from interstellar space. Beyond the heliopause, the sun no longer governs the local plasma. The particles and the magnetic fields are those of the broader galaxy. In late 2004, the leading probe crossed the termination shock at a distance of roughly 94 times the distance from the Sun to the Earth. Its instruments registered the abrupt slowing of the solar wind, the rise in plasma temperature, the change in magnetic structure. 3 years later, the trailing probe crossed the same boundary at a different distance, about 84 times the Earth-Sun distance, confirming that the boundary was not a perfect sphere, but a lumpy, time-varying surface that depended on the activity of the Sun and the local interstellar environment. The 2 crossings showed that the boundary was shaped by something larger than the immediate motion of the solar wind. Modelers, working from the new data, began to revise their pictures of what the heliosphere actually looks like. In August of 2012, the leading probe crossed the heliopause itself. The signature was unmistakable. The density of charged particles around the probe shot up by roughly a factor of 40 as the probe moved from the diffuse plasma of the heliosheath into the denser interstellar medium beyond. The flux of high-energy galactic cosmic rays particles streaming in from outside the solar system, normally partially screened out by the sun's bubble, rose sharply. The flux of low-energy particles from the sun, which had filled the inside of the bubble, fell to almost nothing. The probe had become, on that day, the first human-made object ever to leave the solar system as the sun defines it. The crossing was not announced for nearly a year afterward, while the mission team examined the data carefully and waited for the patterns to stabilize. The announcement, when it came, was measured. The crossing had happened. The probe was now in interstellar space. 6 years later, in November of 2018, the trailing probe crossed the same heliopause boundary at a different location and confirmed the basic findings. But there were surprises too. The boundary was sharper than most models had predicted, more like a wall than a long gradient. The interstellar magnetic field, on the far side of the boundary, was aligned in a way the models had not entirely expected, and the alignment did not change as drastically across the crossing as had been predicted. Even now, more than a decade after the first crossing, scientists are still revising their understanding of what the probes saw. The crossings were not a single event. The probes have continued to send back data from the interstellar medium for years after each crossing. They have detected pressure waves rolling outward through the heliosphere, from solar storms disturbances that take more than a year to propagate from the Sun to the boundary, and which arrive at the probes as a faint, slow shift in particle density. They have measured magnetic bubbles inside the heliosheath that nobody had predicted. They have found, on the far side of the heliopause, a steadier and quieter environment than the solar wind they spent decades inside. But the new environment has its own structure, its own faint variability, its own questions. Each year, the probes return measurements that nobody on the planet that built them could otherwise have obtained. The data is slow. The data is faint. The data is, in the broad sweep of planetary and stellar science, irreplaceable. There is no other instrument inside the boundary on which the probes have crossed. There may not be one again for generations. The probes, while their instruments hold, are the only direct contact the planet that built them has with the region of space on the far side of its own solar bubble. The scientist who advocated for the pale blue dot image had been writing about the deeper implications of planetary exploration for years before the photograph was taken. His argument, made in patient and accessible language across many essays and lectures, was that the long view from outside the planet's own context tends to clarify what is and is not important on its surface. He had used the word perspective carefully, knowing that it could be made trite by overuse. The image, when it was finally taken, made the argument visible. The single pixel of pale blue light, sitting inside a scattered band of optical artifacts in a photograph from 6 billion kilometers away, was the planet itself, framed against an indifferent background. The argument no longer needed to be made in words. The picture was the argument. The text that the scientist later wrote about the image has been quoted in many places, in many languages, over the decades since. The core observation he drew from the photograph was that every person who has ever lived, every act of love and cruelty, every belief, every history, all of it occurred on a single small mote of dust, in a single beam of sunlight, in an unremarkable region of an unremarkable galaxy. His reading was not nihilistic. He drew from the image, instead, a quiet, ethical conclusion that the smallness of the planet in the larger frame is itself an argument for treating its inhabitants gently, and that the indifference of the universe is not a license, but a responsibility. The argument was not new in itself. It was the visible image that gave it new weight. The image is, in technical terms, only modestly impressive. The Earth is a few pixels across at most. The dot itself is less than 1/10 of 1 pixel wide. The scattered light around it is an artifact of sunlight striking the probe's camera optics at an oblique angle. There are countless better photographs of the planet that built the probes, taken from closer distances by other spacecraft. But none of them is the same image. None of them was taken from outside the planetary system. None of them shows the planet at the smallness it actually has, in the context it actually occupies. The pale blue dot photograph, as a single composition, is irreplaceable, not because it is the best image of the planet ever taken, but because it is the image of the planet from a vantage point that may not be reached again for a very long time. After the pale blue dot panorama was complete, the probes turned the remaining instruments outward and began the long approach to the boundary between the solar wind and the interstellar medium. That boundary, the heliopause, had been theorized for decades. Its location had been estimated within broad limits. Its detailed shape had been modeled by many groups, with each model producing slightly different predictions for the structure of the various layered surfaces: the termination shock at the inner edge, the heliosheath as a thick turbulent layer, the heliopause as the outer membrane. The probes were on a course that would carry them through all three surfaces in sequence. Nobody had ever measured any of them in person. The probe's instruments tracked the slow changes in the surrounding plasma as the boundary approached. The solar wind, as the probes moved outward, became thinner and slower. The magnetic field changed in its character. The energetic particle population shifted. The transitions did not occur at the distances the early models had predicted. The termination shock, when the leading probe crossed it, was further out than most pre-mission estimates had suggested. The heliosheath, on the far side of the termination shock, was thicker and more turbulent than predicted. Magnetic bubbles formed within the heliosheath, structures that the standard pre-mission models had not anticipated. The probes were sending back data that did not match the textbooks. The textbooks, after the data was returned, would have to be revised. The crossing of the heliopause itself, in August of 2012, was identified by a sequence of unmistakable changes. The plasma density around the probe shot up by roughly a factor of 40. The flux of high-energy galactic cosmic rays rose sharply as the screening influence of the heliosphere fell away. The flux of low-energy particles from the Sun fell to almost nothing. The local magnetic field, surprisingly, did not change as drastically as the models had predicted. The interstellar magnetic field, on the far side of the boundary, turned out to be aligned much more closely with the heliospheric field than expected. Why this is so is still being debated. The probe's measurement, however, is what it is. The boundary is real. The crossing happened. The map of the solar system, from that day forward, included an outer edge that had been touched by a human instrument. Since the crossings, the probes have continued to return data from the local interstellar medium. They have measured the slow waves of pressure that roll outward through the heliosphere from solar storms, disturbances that take more than a year to propagate from the Sun to the boundary, and which arrive at the probes as faint, slow modulations in the local plasma. The probes have detected occasional larger disturbances corresponding to particularly energetic solar events, registered as a brief brightening and then a slow fading of the local plasma wave noise. They have mapped the variability of the local interstellar environment, showing that what models had treated as a uniform medium is, in fact, modestly structured at the scales the probes can sample. None of these findings, on their own, are dramatic. Together, they make up the first direct survey of the region of space immediately outside the Sun's bubble. The probes have also given the working models of the heliosphere a calibration they did not have before. Before the crossings, modelers were free to assume almost anything about the structure of the boundary within the loose limits set by remote sensing from inside the bubble. After the crossings, the modelers have had to match real measurements at two real crossing points. The shapes of the surfaces the models predict now have to pass through the points the probes actually visited. The constraints have tightened considerably. Some models that were considered viable before the crossings have been quietly retired. Others have been adjusted, sometimes substantially, to fit the new data. The mapping of the heliosphere, as a structure in 3 dimensions, is now anchored at 2 specific places. The rest of the map remains uncertain. But the anchors are real and they will not move. The 2 crossing points are themselves significantly different from one another in ways that have helped refine the picture further. The leading probe crossed at a higher heliographic latitude, in a region of the boundary that is closer to one of the heliosphere's natural symmetries. The trailing probe crossed at a lower latitude, in a different orientation, in a different phase of the Sun's long activity cycle. The differences between the two crossings show that the boundary is not a fixed surface. It pulses gently in and out with the solar cycle, deforms in response to changes in the local interstellar environment, and varies in thickness from one region to another. The structure of the boundary, in other words, is dynamic on timescales of years. The two probes, in their separate crossings, have begun to map that dynamism. Part 7. The long drift after the cameras go dark. The probes are now several decades into a journey that has no end. Each of them is traveling, in the frame of the Sun, at roughly 17 kilometers per second. That speed is fast by human standards and slow by astronomical ones. At that speed, the probes will never enter another planetary system. They will never be caught and pulled into orbit around another star. They will move outward, very slowly on cosmic terms, in directions chosen by the geometry of their last planetary encounters, for as long as the structure of the galaxy permits. Their power continues to fade. Each year, the generators produce a few watts less than the year before. Each year, another instrument must be switched off to keep the rest running. Engineers manage the power budgets with the patience of curators, choosing which instruments to retire next, which heaters to shut down, which subsystems to put into low power modes. The engineers themselves, in some cases, joined the mission as students and have grown grey in its service. A few of the original team members are still consulted on technical questions. Most of the people who built the probes are no longer alive. The probes have outlasted careers, marriages, geopolitical orders, and a long succession of attempts to retire them. Within the next decade or so, both probes are expected to run out of power for their last instruments. The radio transmitters will, at some point shortly after, fall silent, either because the power drops below the minimum needed to send any signal, or because some critical subsystem fails in a way that cannot be worked around at a distance of more than 20 light hours. The exact date of the last transmission is unknown. It will not be announced ahead of time. The silence will be discovered by absence, when the antennas listening at the scheduled time hear nothing. And the silence persists across the next attempt, and the next, and the engineers slowly conclude that the last word has already been said. And then the probes will continue. They will move outward in silence, no longer reporting their conditions, no longer measuring their environment. They will drift through the local interstellar medium at a steady 17 kilometers per second. They will, on a timescale measured in tens of thousands of years, approach other stars. The encounters will be encounters only on a map. The probes will pass at distances of 1 or 2 light years, far enough that the stars themselves will be entirely unaffected, far enough that the probes will register no change. But on the long sky chart of the local stellar neighborhood, the probe's paths will pass close to particular stars at particular times. The leading probe is moving in the direction of an old constellation named for a long-necked creature in early astronomical drawings. In roughly 40,000 years, it will pass within a light year and a half of a small dim star in that general region of the sky. The trailing probe is moving in a different direction. In about 300,000 years, it will pass within a few light years of the brightest star in the night sky, as seen from the planet that built it. Neither encounter will involve any direct interaction. The probes will simply drift past, several light years away, while the stars themselves continue on their own slow orbits around the center of the galaxy. On much longer timescales, both probes will continue to circle the center of the galaxy, swept along by the same general motion as the Sun itself, moving at galactic orbital speeds that take roughly 220 million years to complete a single circuit. The probes will not stay together. Their slightly different vectors will, over many orbits, pull them into different parts of the galactic disk. Each will become a small, dark, isolated body, no longer in radio contact with anything, no longer measuring anything, simply present. They will pass through clouds of dust and gas, through the gravitational neighborhoods of unknown future stars, through stretches of empty space that exist between the spiral arms. They will continue on, in directions slightly different each from the other, for as long as the galaxy itself holds together in something like its current form. Each probe carries, bolted to its exterior, a phonograph-style record made of gold-plated copper, sealed inside a thin protective cover. The records were prepared in the months before launch. Their contents were chosen by a small committee of writers, scientists, musicians, and artists, with the goal of representing to whoever might one day find one of these probes what the planet of origin was like at the moment of departure. The committee worked through long arguments about what to include. The list of what was left off the records is in some ways as interesting as the list of what made it on. What survives is a snapshot of how a small group of people in a particular year chose to introduce their world to anyone who might one day encounter one of these objects in the deep dark. The records contain greetings spoken in dozens of languages, ranging from ancient tongues to common modern ones. They contain sounds of the natural world, thunder, rain, wind through trees, the songs of whales, the calls of birds, the hum of insects. They contain sounds of human civilization, laughter, footsteps, a heartbeat, the tools of work. They contain pieces of music chosen to represent a small fraction of the world's musical traditions, from a single composition by a Western composer of the 1700s to a folk song from a small village to a song of pure rhythm from another corner of the world. They contain images encoded in a slow analog format, including diagrams of the planet's place in the local stellar neighborhood, the structure of basic chemistry, scenes from daily life, and the silhouettes of human bodies. Each record carries, etched on its outer cover, a diagram of how to play it. A stylized arrow points to a stylized stylus. A reference to the spin rate is given in terms of the natural frequency of the hydrogen atom, a unit any sufficiently advanced civilization should recognize. And a map of the relative positions of 14 pulsars, as seen from the solar system at the time of launch, gives a kind of postal address for the planet of origin. The 14 pulsars vary in their pulse rates in known ways. Any sufficiently advanced civilization that found one of the records could, in principle, locate the solar system at the era of launch by comparing the pulsar pulse rates encoded on the record to the pulse rates of those same pulsars as they would observe them, working backward through time. Whether the records will ever be found is unknowable. The probability of any small object drifting in the immense space between stars being encountered by another spacefaring civilization is, by any reasonable estimate, astonishingly low. The probes are stable. They are sealed in materials chosen for their long-term durability. Their golden records, bolted on, are expected to remain legible for hundreds of millions of years, possibly billions, far longer than any civilization on the planet that launched them will likely persist in its current form. The records will almost certainly outlast the Sun's stelliferous lifetime as the planet that built them currently knows it. They will drift through the galaxy for cosmic time. They are, in a quiet and entirely literal sense, the longest-lived artifacts the planet has ever produced. The promise in the title of this video, that the probes found it has, in the body of the video, a quiet documentary answer rather than a single dramatic reveal. What the probes found, across nearly half a century, was that the solar system is far stranger, more active, and more varied than any prior model had predicted. They found that Jupiter is a planet of perpetual storms, and that one of its moons is the most volcanically active body in the solar system. They found that another of Jupiter's moons may hide a global ocean of liquid water beneath its ice. They found that Saturn's rings are not 5 rings but hundreds, and that they are slowly disappearing. They found that one of Saturn's moons has a thick organic atmosphere unique in the solar system, and another conceals a global subsurface sea. They found that Uranus rolls along its orbit, that Neptune carries the fastest winds anywhere in the solar system, that Neptune's largest moon orbits backward and is geologically active despite its extreme cold. They found the edge of the solar wind, the boundary between the sun's bubble and the interstellar medium, the layered transitions between the two. They found a sharper and stranger heliopause than the models had predicted. And they found, simply by being where they were, that the Earth is a single pixel in a much larger frame. Every answer the probes have produced has arrived alongside 2 more questions. That is how they have rewritten the planetary science of the outer solar system. Not by closing the chapter, but by showing how much more chapter there is to read. The fade is slow. The silence is approaching. But on this evening, as anyone watches or listens, both probes are still out there, still moving outward, still in the oldest and best sense of the word exploring. And so we leave the 2 probes where they are moving outward through the long quiet, no longer reporting, no longer measuring, simply continuing. The records bolted to their sides will outlast the worlds that made them, and the dot of pale blue light in the photograph will continue to circle a quiet star, whether anyone is watching or not. Let your breathing slow. Let your shoulders soften. Sleep well, and good night. The long drift the probes are now on does not begin at any single moment. There is no instant when the engineers can say the planetary mission has ended and the interstellar mission has begun. The transition is gradual. The cameras went off in 1990. The dedicated planetary instruments went off in the years that followed. The heliosphere instruments are still running, decades after their nominal end of life. The mission's character has shifted slowly across decades, from a planetary tour to a deep space survey to, eventually, a slow, patient measurement of the local interstellar medium. Each phase has overlapped the next. None of them has been formally announced as the end. The engineers themselves, in interviews and meetings, have described the work as a single continuous mission whose nature simply changes over time. Within the next decade or so, the engineers expect to begin retiring the remaining instruments one by one. The plasma wave instrument may go first, then the magnetometer, then the cosmic ray subsystem, in an order that depends on the power available and the relative scientific value of each instrument at that point in the mission. The exact sequence is being planned now. Each retirement is a small ceremony, a small acknowledgement that the mission is being slowly closed down. The engineers know this. They speak of it openly. There is no pretense on the part of the people who have managed the probes for decades that the silence is anything other than approaching. The transmitters themselves will fall silent at some point after the last instrument is retired. The transmitter is one of the most power-hungry subsystems on each probe, and once the science instruments are no longer drawing meaningful power, the transmitter will not be far behind. When the transmitters go quiet, the probes will continue to receive any commands the engineers send for as long as their command receivers continue to work, but they will no longer reply. Eventually, the command receivers, too, will fall below the threshold required to operate. After that, the probes will be deaf as well as silent, and the engineers on the planet that built them will have no further contact with them. The probes by then will be moving outward through the local interstellar medium with no further attention from anyone. What happens after that is not a question for engineers. It is a question for the long sweep of cosmic time. The probes will drift through the local interstellar medium at their steady speed for thousands of years, encountering nothing more than the diffuse gas and dust between stars. Occasionally, on a long enough timescale, the probes will pass close by interstellar standards to other stars. Those encounters will not affect the probes in any meaningful way. The probes carry no light source. They emit no signal. They are inert. They will pass at distances of several light years, far enough that the gravity of the encountered stars will barely perturb their motion. The encounters will be encounters only on a map, only on the page of a future astronomer if such a person ever traces the probe's paths. On still longer timescales, the probes will orbit the center of the galaxy alongside the other stars of the local stellar neighborhood. The galactic orbit at the Sun's distance from the galactic center takes roughly 220 million years to complete. The probes will not complete many such orbits before they are scattered by the gravitational influences of passing stars, dragged into different parts of the disk, eventually lost from any short list. They will not, in any reasonable estimate, leave the galaxy. They will simply become indistinguishable parts of the long, quiet population of small, dark bodies that drift between the stars, no longer carrying any signal of who built them or why. The records bolted to their sides, however, are made of more durable material than most of the rest of the probes. The gold-plated copper of the records is chosen specifically for its resistance to the slow erosion of cosmic radiation and micrometeorite impacts. The contents of the records, the music, the greetings, the photographs, the diagrams, are etched into the surface in a way designed to survive for hundreds of millions of years, possibly longer. The records will be readable, in principle, for cosmic time. They are the longest-lived objects the planet that built them has ever produced. Whether they will ever be played by any audience other than the engineers who designed them remains an open question. The probability is, by any reasonable estimate, very low. But the records are stable. They will continue to drift through the galaxy for as long as the galaxy itself holds together. The pulsar map etched onto each record is the closest thing the planet that built the probes has ever made to a permanent address. The 14 pulsars on the map all have known pulse rates, and those pulse rates are slowly slowing down over time in known ways. A sufficiently advanced civilization that found one of the records, even far in the future, could in principle look up the current pulse rates of those same 14 pulsars, compare them to the rates encoded on the record, and calculate when the record was sent. The calculation would give them a time of departure. The geometry of the 14 pulsars on the map would, in turn, give them a place of departure, the position of the Sun at the moment the probes left it. The address is approximate, but it is genuine. It is the planet's signature, etched in gold, traveling outward at 17 kilometers per second. The probes themselves have no opinion about any of this. They are small, durable, patient machines. They do their work as they were told to do it. They continue moving outward because nothing has stopped them. They send back what their instruments measure until they cannot. They carry, bolted to their sides, the long, quiet record of a small planet's brief moment of looking outward. They are the longest reach the planet that built them has yet achieved, and they will, for as long as anyone alive on the planet can be expected to know about it, remain so. Whatever the planet does next, the probes are already past the edge. They are already on their way. There is, in the long fade of the mission, something that is easy to overlook but worth pausing on. The probes have spent more of their existence outside the heliosphere than any future mission is likely to spend inside one. The boundary they crossed is, in cosmic terms, a thin shell. The interstellar medium they now drift through is the dominant environment of the galaxy. Stars are rare. The space between them is vast. Whatever else the probes are, they are now creatures of that vast space, rather than of the small bubble around a single star. They have, in a quiet sense, joined the long majority of matter in the galaxy that lives between stars rather than near them. If the probes had been built to do nothing other than reach this place and stop here, they would have justified themselves on that fact alone. They went past Jupiter and Saturn, past Uranus and Neptune, past the termination shock and the heliosheath and the heliopause, past the long gravitational tail of the Sun, into the long quiet of the local interstellar medium. They are no longer travelers within a planetary system. They are travelers between stars, even if the stars they pass remain forever distant. The fact that they continue to send back data from that place for as long as they can, at the rate they can, is, in the long view, a small bonus on top of the larger achievement of simply being there.